of xenoliths, tens of thousands of them. So they're very important localities to try to piece together what's happened in the upper mantle and lower crust. The word xenolith, the roots of the word xenolith indicate foreign rock fragment. Xeno means foreign and lith is rock. These are rocks that do not belong to the lava that brought them to the surface.
Xenoliths were once part of the bottom of the Earth's crust, and even part of the mantle. They formed the deep inner lining of volcanic conduits. When volcanoes come to life, rising magma rips chunks of rock from the lining and carries them to the surface.
When you see the lava at the surface, you will notice different looking rocks in it, maybe little white and black rocks that come from deep in the crust, or those fascinating little green beauties, little granular green clusters, which are pieces of the mantle.
Xenoliths are important because they give us a direct look at the bottom side of the continent. With the help of machines like the electron microprobe, xenoliths reveal a fascinating new picture of the bottom of the Earth's crust. Traditional theories hold that the crust ends abruptly where it meets the denser rocks of the mantle. This neat, sharp boundary is nicknamed the moho. But xenoliths show that the moho is a bit messier in volcanic regions. Magma from the mantle often rises to the bottom of the crust, but then goes no further. The moho is obscured. Scientists recently learned that this was the start of an important process of crustal thickening called underplating.
Underplating is a process by which magma that's generated in the Earth's mantle is added to the Earth's crust, but at the base of the crust. Normally we think of magma as rising all the way through the crust and coming out at the surface at volcanoes. But with underplating, instead of it making it all the way to the surface, it actually stops and ponds right at the base of the crust where it contacts the upper mantle.
Eventually, the magma from the mantle hardens to rock and becomes new continental crust. In this way, underplating makes the crust grow thicker, from the bottom down. It turns out that underplating has added new crust to the bottom of continents all over the planet. Here in the Alps of northern Italy, geologists can actually see where this happened millions of years ago. This is the Ivrea Verbano zone, a rugged place where geologists must also be expert rock climbers. The Ivrea zone is near the boundary where two crustal plates meet, the European and African plates. Millions of years ago, Italy, a part of the African plate, was an island in the ancient Mediterranean Sea. The African plate then moved north, causing Italy to dock with the continent. During the collision, rocks of the ancient seafloor had nowhere to go but up. They now rise more than 12,000 feet above sea level in the Dolomite range of northern Italy. Geologists once thought that the entire thickness of the crust rose out of the ground here, exposing the moho. The Ivrea Verbano zone was a place where the moho could be seen. The moho was thought to be so sharp a line that one could put a finger on it. It appeared that crust rocks were on one side, mantle rocks on the other. But the more geologists studied the area, the less this theory seemed true.
Questo campione è stato preso qua sopra sulla moho o ex moho.
It began to look as though all the rocks here were crustal rocks. Perhaps this was one of those places where mantle rocks had been transformed into crustal rocks by underplating. To find out for sure, geologists took hundreds of rock samples back to the lab for analysis.
Okay, Ben, I think we're ready for the pressure vessel.
Okay.
In lab experiments, the Ivrea rocks were subjected to the extreme conditions that exist at the bottom of the Earth's crust. Temperatures down there reach 1,200 degrees Fahrenheit, and pressures are 10,000 times greater than at the surface.
Time for the end load. Okay, Ben, here we go.
These experiments confirm that underplating did indeed take place at the Ivrea Verbano zone. Scientists have also learned that underplating and other processes happening in the lower crust can have major effects at the Earth's surface.
Well, we know that there's lots of things that go on down the lower crust of the Earth, and many of these things have a profound influence on us as humans in the surface of the Earth. Rocks and minerals change when they're subjected to heat and pressure. Rocks can melt. The minerals in the rocks can change themselves into denser minerals, and so the rocks themselves become heavier. And all of these things manifest themselves on the surface of the Earth. Rocks melting give rise to magmas, which are implicated in explosive volcanism. Minerals in rocks can dehydrate, giving rise to water and CO2, which are implicated in the formation of gold and silver and copper deposits. All of these processes, which have their origins deep in the crust, manifest themselves on the surface of the Earth in ways that are very important to our survival as human beings or to the longevity of our civilizations.
In the San Francisco Bay Area, the crust-mantle boundary plays a role in a destructive scenario. In the Loma Prieta earthquake of 1989, damage was heavy in and around San Francisco. But the quake's epicenter was more than 60 miles away. In between, relatively minor damage occurred. It turns out that loose soils were a factor in the severity of ground shaking in San Francisco. But scientists think there may have been another factor. Some seismic waves generated during the quake went down, struck the Mojo at an angle, and then bounced back under San Francisco. Apparently, these bouncing waves were more destructive than waves traveling straight through the Earth's crust. A large quake is predicted to strike the heavily populated east side of San Francisco Bay, which lies above the Hayward Fault. Because so many people are at risk, earthquake scientists conducted an experiment to predict what might happen when that quake finally strikes.
From the 1989 Loma Prieta earthquake, we noticed that indeed seismic energy does go down, strike the Mojo, and come back underneath San Francisco. We wanted to see in the East Bay along the Hayward Fault if a similar type phenomenon would occur. And since we can't wait for the next earthquake, one of the things we did is went out and generated our own. We put explosive sources in high probability areas that we know are very likely to generate a large earthquake in the near future. And we wanted to see how the energy would travel from those locations to the north in Berkeley, Oakland, and the populated areas, and also to the south in the San Jose area.
7, 6, 5, 4, 3, 2, 1.
From the southern Hayward, if we were to have a large earthquake, seismic energy from that earthquake would travel down, strike the Mojo, and surface underneath the Oakland, Berkeley area. And from our indications, the shaking would be very intense, much more so than was observed from the 1989 Loma Prieta earthquake coming under San Francisco.
To scientists, earthquakes are a source of invaluable information. When a big quake occurs anywhere on Earth, scientists get a glimpse of the entire inner structure of the planet.